section D, probably we are going to arrive up to here. Okay. Separable differential equation. What do we mean with separable? When you got the function, the y dx is equal a function where this function can be a function of x and y. But if you can separate like this, the y dx fx dy, you can separate like this, then we call that is separable. So this case is separable. The y dx is x, one part depends only on x, and the other part depends only on y. This is more easy because this only depends on y. Okay, so it's very easy. It's like the first we do, and all of this. Probably the best thing to do is put an example where it's not separable. I'm going to put it like this. An example where it's not separable. The y dx equal to sine of squared plus y. Now this function you cannot separate. Are you understanding what I'm trying to say? You cannot separate this function because x and y are involved in the same function. You cannot separate. You cannot put it like this. And then this is going to be harder to solve. Perhaps, I don't know, because I am not differential equation teacher. What the course I teach at electrical engineering has to do a lot with differential equation, but more of them linear differential equation. And this is a non-linear differential equation and is not separable, and I don't know if there is one method to solve it algebraically. Probably I will do it by numerically at the computer with Euler, but Euler is a very bad method. It's a very method, easy to understand, but very bad. Okay? Not separable. But what happens when they are separable? What happens when they are separable? That you can do this. When they are separable, this is all the signs that is here. You are gonna take the y to one side and the x to the other side. This is what we did, for instance, with this. This is separables. dp dt equal 3p. It was an example of separable. Because I can put p, the variable p to this side, the variable t to the other side. Remember part here that p is y, t is x. Yes? Remember, no? This is our first model that we solved today, and it gives us the result an exponential growing function, growing exponential function, exponential growing function. I am just interchanging, yeah? That means I already tired, because I know when I'm tired, I'm tired, because I am not very used to talk 2 hours English continuous every time, you know. So it's a little bit of yeah. But you understand, yes? And then what happened when you separated? Well, that you had two integrals. You had to integrate this part and you had to integrate that part. It's more or less the same. This is not difficult. The difficult part is going to be a section that is ahead, that is called the integration factor. This is the only part of this chapter that is really difficult, besides the integrals, okay? So for instance, you got these two examples that are very easy to follow. Um, dy dx is equal x multiplied by y, and then you can put y to here, and dx to the other side, then you get to this part. And then this is easy, because this integral is logarithm, natural logarithm of absolute value y. And this integral is very easy because it's a polynomial. It's 1/2 squared plus c. These are very, very easy examples. And then you can say, well, y equal e elevated to this. Why do they put plus or minus here? Because when you got absolute value, if you want to, yes, you can put it like this. This part, you understand? Yes? Well, you get the fact that you have here absolute value when you want to go to y, and then the two solutions are possible because the two solutions with plus or minus are going to give you the same absolute value. But this is irrelevant because at the end, what you have to see is that if you got here, again, you are going to separate this in the part that depend on x, and it's like that. What we did before, if I have e elevated 1/2 squared plus c, I can put this like e to 1/2 squared multiplied by ec. That is a constant. Yes. Ec multiplied by plus minus, I can say is another constant. And then I get to this solution. Yeah. How do I find A with a boundary condition? They have to give us what I say boundary condition, because not always the condition is given at the zero value. It can be given in another value. When we are solving in time, when we are solving a differential equation in time, normally it's given at the initial condition. What is the value of the variable at the t equals 0, and what happened with her, with the variable afterward? What is the behavior of the variable for t greater than 0, starting from an initial condition? But this is only for differential equation in t, but mathematical is wider than that. Mathematics include every cases, all cases, and you can have another kind of differential equation that the independent variable is not t. So in general, we talk about not initial condition, we talk about boundary condition. Okay? How you can verify? Well, very easy, because if you got here y, you got this. I don't want to go from this to, because I don't want to open another book for that. But if I got this, what happened if I derivate? No? And what happened with this solution? I got this solution here. Y equal a elevated 1/2 squared. What happened when I differentiate this? Dy dx is going to be, when I differentiate, it's going to be a multiplied by the derivative of e elevated to this. But by chain rule, the derivative of the power is going to be 1/2 multiplied by 2x. 1/2 with 2 goes with 2, and you're going to have a e. Yes? Are you understanding what I'm talking about? I am differentiating this equation. I am using chain rule. Yes? dy dx is a constant, the derivative of a function, exponential function elevated to another function on x. So it's going to be e elevated to that function multiplied by the derivative of that function. And the derivative of this function is x. Now you are understanding. Chain rule. Chain rule is key. Chain rule is key for learning how to differentiate and to learning how to integrate. Chain rule. What happened here? Well, what happened here is that you have it because this part is y. So you got here the y dx is x multiplied by y. So the differential equation. This differential equation has this solution. I'm gonna do the other one by better in the oh, esta es una maravilla. I like this class. Why I like so much? Because this new app is what I've been looking for. It's like my new girlfriend. Okay, this is also a case of sorry. It's also a case of separable variable. Well, it's separable. It don't got x, but it's separable. It's a special case of separable variable. And this is easy because you can put y squared for that. Y squared di equal dx. No? It's like multiplying in cross multiplying. And then you integrate square dy equal the integral dx. And then this is gonna be uq over 3. This is, you know, as always, they used to yes. And the last part, if you want to see, is you can isolate from here because the solution has to be expressed. It is possible, no? Sometimes it's not possible, but in this case, possible instead of y. Say, I can pass this to there like 3 is 3x plus c, okay? And then y is gonna be s cubic root of 3s plus c. Again, here the integration content. What you are finding? A general solution, a family or infinite solution, a family of solution. You give me the initial condition. For instance, y de 0 equals 0. Well. Then you find c. C is going to be 0 in that case. For it's an instant, no? But really the problem, going back to the problem, they here is finding the general solution. So, okay. Here, this is another example. This is another example with boundary condition. Yeah? And then when they give you boundary condition, you have to go one step more. Yes? First, you solve the general solution, and then you apply the condition. And then again, here you got this function, but this function is separable. Why is separable? Because you got this, the function of y, and here, the function of x. And then you pass this part to this. This is what you are seeing here. You go a elevated 2y, you put it like here, divided, and cosine 3x, and then, well, they go all of these, but it's the same at the end. Yes, dy dx multiplied by dx. It's more formal, but it's gonna be the same. We normally say dx pass to this side, but this is the formal way of telling the same. Are you understanding what I'm trying to say here? Okay, it's the same. So 1 over e is down, but it's indicate exponential functions are nicer functions. This is e minus 2i. So you got here, and these are two immediate integral. Remember, the problem of differential equation is going to be as hard as the integral involved. Normally, they don't put so much hard integral. We have to see some problems. I have seen problems of A level, further math, and sometimes are difficult, the integral. But I don't know IB, because I had not Okay, perfect. That's the way you do it. Now you are understanding the past. This is immediate integral is minus 1/2, no? Because if you derivate this is gonna die. Again, why minus 1/2? Because you got to put here outside minus 1/2 to get here minus 2. That is the derivative of minus 2i. Yes. Are you understanding what I'm trying to say, or you are tired so? And here to say, why want, and here 1 over 3. Why? Because you got here 1 over 3 to put inside 3, and then you got the derivative. And then you got, you isolate, and then you apply logarithm, natural logarithm to isolate y, and then you solve, and you get this horrendous equation. It's horrendous. It's minus 1/2 natural logarithm of minus 2 over 3 multiplied by sine 3x plus c is horrendous, but it's not as horrendous as it looks, because you were able, or we were able to solve it algebraically. The really horrendous are the ones that you cannot solve it. And then with this result, you apply the initial condition. Y0 equals 0. So it means for x equals 0, they are telling you that y should be 0. So what you do is equate 0. You substitute here for x equals 0, sine of 3x for x equals 0 is 0. So you have put here 0. Then all of this is going to go, it's going to have minus 1/2 natural logarithm of c. That means natural logarithm of c is equal 0. That means c equal 1. And then you have the result. This is the particular solution. One thing that I want you to go away from this class is understanding pretty well what's the difference between general solution and particular solution. Do you understand that?